Hello, everyone. I'm Pierre. Some of you may know me as GhostDogPR on GitHub and Discord. You might have seen my avatar a few times, maybe first time you see my face. I've been contributing to Zio in the early stages, and then I created Caliban 3 years ago. And recently, I've open sourced a new library called Shardcake, which I'm going to talk about a bit later. I work for a Korean gaming company called Devsisters. Especially, I work on a game which is a mobile multiplayer RPG/city building game called Concurrency Kingdom. We launched the game 2 years ago, and it has been pretty successful with over 40, nearly 50 million users. You can try it. It has an English version. Maybe your children might like it. And what's nice about it, it's entirely made with functional Scala and using a lot of libraries from the Zio ecosystem. Okay, so to talk about sharding and explain what it is, I'm going to take a simple example and a use case. So let's say we want to build a multiplayer game. And in that game, our players can create and join guilds. And we have one constraint, that is a guild cannot have an unlimited number of players, so it is limited. And of course, because it's a game, we want to be able to have a lot of users, so we want to be able to scale out and have as many game servers as necessary. By the way, even though we take this gaming example, what I'm going to talk about is applicable to any system where you have concurrent access to something, basically. Okay, so let's implement the logic for joining a guild in a very naive way. So when a user wants to join a guild, the client connects to a game server, then the game server will process loading the guild, verify if the guild is not already full, and if it's not already full, we are going to accept it and save the new member into the state. But what happens if two players try at the same time to join the same guild, and the other request for the second player goes to another game server, and maybe that other game server is going to do the same verification at the same time, and they both might accept a new user, and then maybe our guild had only one spot left, and now it's going to be full. So how do we deal with this kind of problem in a distributed environment? One option is to use shared lock between different servers. So when you have two different servers who want to write the same entity, the first one will go through, and then the second one will wait for the first one to actually finish before it can process. That way, the first one can succeed and the second one can fail in our example. This in legacy servers have usually been implemented in the database layer, but these days it's not really something that people want to do anymore. I'm sure all of you would rather write your business logic in Scala rather than in SQL. And also it leads to a lot of complexity, because then you have one lock and then you have multiple locks, you can have deadlocks. So I think this is a bit out of fashion today. The other option is what I call the single writer pattern. So instead of having multiple components trying to write or edit the same thing, you redirect by some way all the requests about a single entity to a single component, and that single component will handle requests one by one in order. So here is an example of how it would work here following this pattern. So the game server 1 that received the first request would redirect by some way to another server, let's say game server 3, and then the second one will redirect the request to the same game server 3 as well, and then the game server 3 will process them one by one. So how do we implement that in practice? Can't we just use Kafka? Isn't Kafka doing exactly that? There is a feature in Kafka called consumer groups, and basically you have multiple consumers in a group and messages with the same key. So messages, for example, in our example here, messages for the same guild will be going to the same consumer. So that works really well, and actually we are using this pattern for a lot of different things. However, in some cases, it's not 100% a good fit. For example, Kafka persists messages, but if you're just redirecting messages, you don't really need them to be persisted. And then the most important point, I think, is that Kafka is good for asynchronous workflows. So you have your publishers publishing data, and then you have your consumer consuming it, and they are kind of decorrelated. But sometimes, when you have a synchronous workflow, you want a response immediately to your request. And in that case, you don't really want a consumer to eventually consume it and respond later. You want it to be as fast as possible. You can configure Kafka for optimizing latency, but it's still a little not practical. You also need to have like a topic for responses. That's a little bit annoying. So there are some other options. The main option that was used so far in the Scala and Java ecosystem is Akka Cluster Sharding. So how does it work? When you use Akka Cluster Sharding, all the nodes form a cluster, and then entities or actors are grouped into shards, and those shards are dispatched onto different nodes in the cluster. So when you send a message to a particular entity, like our guild, Akka Cluster Sharding takes care of redirecting it to one particular node in charge of this entity and other entities on that shard, and then it can respond back to the sender. It's using Akka remoting, which is their own protocol under the hood. So when we launched our game 2 years ago, we were actually using Akka Cluster Sharding. Some of the good points about it is very easy to get started. They have a fantastic documentation, so just by looking at the documentation, it makes you want to use it. And it gets the job done. However, maybe many of you are working with a more functional programming style of Scala, and Akka is not using this paradigm, so it's built on top of Future. So if you use functional FP or ZO, you will need to mix pure and impure code back and forth, so it's a little impractical, but it can work. Or you can also use something like ZO Akka Cluster, which is a wrapper around Akka Cluster that hides the impure parts to expose a pure API. But then the trouble started when we deployed into production. And we found out that the Akka cluster is really fragile. So it doesn't really like sudden topology changes, such as adding a lot of nodes or removing a lot of nodes at the same time. And it doesn't like network issues, like loss of connectivity between the nodes. Basically, there is a component called a split brain resolver that is in charge of downing nodes that are considered to be out of the cluster. And we found that this was triggered. There was a lot of false positives, and it triggered downing nodes when we didn't want to, just because we added or removed many nodes, or because there was network issue. And several times it happened that after downing one node, it downed another node, and then it downed everything. And in that case, the only solution is you have to like bring down the whole cluster and restart everything. That's a manual operation. If you have nodes individually like restarting, the cluster is corrupted and it doesn't recover by itself. Another thing that we witnessed is that when we did rolling updates, the time it took for rebalancing nodes from the old servers to the new servers was a bit slow, so we had timeouts during rolling updates. Finally, it was pretty difficult to troubleshoot. You can enable debug logs, but then you have like millions of logs. And the logic about the split brain resolver is a bit of a black box. You can't really configure it. So that proved quite difficult for us. There's one more thing that I didn't mention so far, which is the recent announcement that I'm sure you've heard about. And I just want to emphasize on this and that. A small simulation on our set of servers showed that it would be in millions US dollars. I'm sure you can have discounts, but that's not something that you really want. So we decided, and way before actually that announcement, we decided to make our own. So one of our main business design decision was, let's not have a cluster. That Akka cluster was really stressful. We were always afraid that it was going to disappear. So we decided to decouple the application servers from the membership management. We wanted the algorithm for the shard assignment and rebalancing to be as simple as possible so that we could understand it first and tweak it as we needed. And we decided to rely on Kubernetes to handle the health of the node. So instead of the split brain resolver and so on, Kubernetes already has membership. It already has a way to see if nodes are alive or not and to down nodes or add nodes as needed. So we decided to just rely on that instead to add our own cluster membership on top of that, which is basically what Akka is doing. So we came up with an architecture like this where the two main components are the pods here. So those are our application servers. That's where the entities or actors are running. And then we have a separate component that's called the shard manager that has a single instance. And when pods are starting or stopping, they just register themselves and unregister to the shard manager. And the shard manager is in charge of assigning shards to those pods by telling them directly. On top of that, we have that storage layer that is used to store the assignments so that if the shard manager stops and restarts, it's not lost. And the pods are also using that storage layer to get assignments and get updates when assignments are changed. And finally, we have the health API, which in our case is Kubernetes, which is an API that tells us if a node is alive or not. And this is important because if a node is alive, we don't want to rebalance any actor that's on that node because we don't want to end up with the same actor in multiple places. So we rely on that to know if the node is really out, if it's really down, to finally redirect the shards on that node. You might notice that I just said the shard manager is a single instance, so isn't this a single point of failure? It's true that it's a single instance. However, it's actually only involved when new nodes are started or stopping. So it's not at all involved for the communication between the pods. All the pods have a local cache with the assignment, so they know for a given entity, they know which pod they need to talk to. On the other hand, in addition to that, the shard manager is a very lightweight process, so it's really easy to start a new one. Like it can start in a matter of milliseconds if needed. Okay. Once we developed this system, as you can imagine, it was a pretty risky change because we were already in production with a lot of users. So we did a lot of testing to build confidence before we deployed that and replaced Akka, basically. So we did performance tests. We found that it was basically the same with Akka. We did a lot of rolling update tests where we came up with some improvement. As you can see on the picture on the left, our first tries, so this shows the number of entities per node, and you want them to be perfectly balanced. At the beginning, we saw that during rolling updates, you had nodes with too many entities, and then we figured out how to make it really well balanced. And we also did a lot of failure testing. So we tried like killing nodes violently, reducing the network bandwidth, like losing packets, adding delays and so on. And that's where it really shined in comparison to Akka because nodes are not a cluster anymore. So if the network is bad, you might have timeouts or you might have message loss, but as soon as the network recovers, it just works. So it recovers instantly. We released to production on February of this year. It went really smooth. We had no more network-related incidents so far. Another thing that's good is rolling updates are really faster because before we were so afraid of the Akka cluster going crazy that we were adding and stopping nodes one by one. Now we are able to like add or remove a lot of nodes at the same time. And for that reason, we also enabled auto-scaling. So we are saving a lot of money because before, for the same reason, we always had the maximum amount of nodes just to be sure that it was going to be able to handle the load. But now we are like reducing to a minimum, and just when the load increases, we can add nodes. It's totally fine to like double the number of nodes suddenly or reducing as well. And in September of this year, we decided to extract this code from our game code base and release it as an open source library. So here is Shardcake. Yeah, let me show you a simple example, like how to use Shardcake in 3 steps. The first thing is define the message type. So that is the message that you're going to send to your entities. So you define a seal trait. If I keep the guild example that we saw before, you can have 3 types of guild messages. One is join, one is timeout, one is leave. Then you create an object guild that extends this entity type, and you give it what is the message type, and a single string that's basically an identifier that needs to be unique across all your entities. That's really simple. That's exactly the same with Akka, by the way. And then you define a behavior. A behavior is what happens on your entity side. When you start your entity, it can receive messages, and what is it going to do? So as you can see, by the way, this is using Zio, so all the types might be familiar if you're used to Zio. So a behavior is a function that takes an entity ID. So for example, for our guild, it's our guild ID. And then you have a DQ of guild messages. So a DQ is a queue that you can only take from. You cannot push it, offer to it. And it returns a RIO of sharding and nothing. So what does it mean? RIO means it can fail with an exception. It requires an environment of type sharding. And then it returns nothing. Returning nothing basically means that your effect will never stop. It's supposed to be a loop that never stops. So it's supposed to basically consume your queue and do something with the messages. What you do with those messages is entirely up to you. Shardcake is not responsible for that, so you can use event sourcing, you can use whatever business logic process that you want. That's outside of the scope of the library. The library is just there to start your entities on different nodes and redirect messages to it. You basically, it makes it simple to send messages to your entities regardless of where they actually are. But the handling of messages is up to you. And finally, how do you use that? First, you need to register the entity. So you say sharding.register entity basically says this node is able to run entities of the type guild, and here is my behavior. So here is what you need to start when an entity starts. There is also the terminate message here is for a clean stop. If you want to close some things like before the entity is stopped, you can handle it that way. And then sharding.register scoped, or just register, is telling the shard manager this node is able to host entities. You can call register and unregister manually. If you use register scoped, it's going to unregister for you. And then you get this object by using sharding.messenger. You get a guild object, and using this messenger object, you can send message to guild, addressing them by ID. So here there are a few examples below: guild.send guild1, and then join. It's going to send the join message to that guild. So you can send that to like multiple nodes at the same time, and all those messages are going to end up on the same server. All right. One thing we did when we extracted all that code from our code base is initially we made some technical choices. So we were using Redis for storage, gRPC for the messaging between entities, Cryo for serialization, and Kubernetes for the health check. All of these have been extracted into simple traits, so you can provide any implementation that you want. So if you don't use Redis, if you use another storage, you can just provide your own implementation of the storage trait and use your own storage. Same with the three other. So it's not tied to any of these technologies. If you use AWS Fargate, if you use the Desert serialization library or whatever, you can also use them. Okay, just a funny story to finish. I was initially planning to reveal this library today, but with the Akka announcement, which happened one day after I actually published the library to Maven, I decided to just release it earlier. And thanks to Lightband announcement, it got a lot of interest very early on. So thanks to that interest, there are already some interesting contributions that were added by external contributors. So I want to thank the 9 first contributor, well, the 8, because one is me, other contributors, especially Gregor here, who added a distributed pub/sub implementation on top of what was already there. So it allows you to broadcast messages to all the pods in the system. not by ID, just like send to all, which is actually really useful. For example, in our case, we have some caches on all nodes, and if you want to reset those caches, you can directly publish a message to all of them using this distributed PubSub, so that's really convenient. There were also a few other contributions allowing you to customize like some things like how to transform a shard ID, an entity ID to a shard ID, or also improvements of resilience and logging. All right, that's it for my presentation. So if you are curious about it, I encourage you to look at the website. There are a lot of examples. There are some detail about the actual shard assignment logic and rebalance logic, some architecture diagrams, a list of everything that you can configure. You can find me on the ZO Discord. There is a Shardcake channel where I am. So if you have questions, also until tonight I'm here. So feel free to find me and give me any questions. All right, I hope you will find it interesting, and thank you for your attention.